Hi. When I first started learning about refactoring, the question I had in mind was these techniques sound really interesting, but will such incremental improvements actually going to make my code more readable? I was really skeptical. But as time has progressed, I've gotten to learn that even simple techniques like extracting methods or renaming variables can improve the code quality by leaps and bounds. Today, I want to demo a short refactoring which will show us how we can take an unreadable code, which would take us maybe 15 minutes to understand, and with the help of simple refactoring techniques, convert it into a code which barely takes less than a minute to understand. Let's see how we can go about it. I'll introduce the problem to you. I have a programming contest like code. The first two lines here read an input n. The next few lines do some processing based on this input. And finally, we have an output which is either true or false. That is all we know about the problem right now. And our aim is to refactor and try to understand what this code is doing. So let's get started. As a first step, I'll divide this code into three distinct parts: input, logic, and output. I want to do this because I want to focus all my refactoring efforts on the logic part. As a next step, I want to make sure that I don't break any code when I do refactoring. I'll run this code for a few different inputs and I'll note down the outputs. And at the end of it, I will have a list of input versus output. So every time I perform a refactoring, I can run the code again and again and make sure that I've not broken anything. So let's quickly do that exercise. I ran this code for a lot of different inputs, and I have this list of a few random numbers versus their output ready. So for 1, 2, and 3, my output is false. For 4 and 5, it is true, and so on and so forth. So when I do a refactoring, I'll check my code against a few of these to make sure that it is working fine and I've not broken anything. I've identified my first point of refactoring. If you look at this variable O, we check if it is 1, the output is true, otherwise it is false. If you look at the logic part, O is initialized to 0 and it is changed to 1 in one place. Other than that, O is not used anywhere. This essentially means that O is acting like a flag. This flag has only two values, 0 or 1. We'll change it to a Boolean. So instead of checking whether O is 1, we can simply print O here and it should give us the right output. So let me quickly do that. I'll run my code for a few different inputs to make sure it continues to work. I've checked my code against a few different inputs here. If you want, you can check it for all of them. I'll rename O to output to better represent what it is. As a next step, I want to extract this logic part into a separate function. I want to do that for two reasons. The first is I want the main function to be smaller than what it actually is right now. The second is if I can extract this logic part into a separate method, maybe I can write a few unit tests for it based on the input and output list we've created. Once I get that, I'll not have to manually run the code again and again every time to see if it's still working correctly. I can just simply use unit tests and make sure that I've not broken anything. So I'll use the IntelliJ shortcut to extract a method. Since I don't really know what this method is doing, I've just called it do something right now. Once I refactor it further and I understand what this code is exactly doing, I'll rename it to something better. This is a good point for us to write tests for this function. So I'll change its visibility from private to default and then write a few tests for it. To save time, I have already written commented tests for the set of inputs that I had shown you before. So let me uncomment these tests and run them. If they run fine, then the next time we do a refactoring, we can just run these tests again to verify that everything continues to work. So my tests are working fine, and this tells me that going forward, all I have to do is run these tests again once I do a refactoring, and that will give me the confidence that I've not broken anything. Let's try to see what our next refactoring can be. Typically, when I have such a long method, what I try to do is look at the for loops, the if conditions, and see if I can extract them into separate methods. What I also try to do is I see variable names like f and see if I can rename them to something better. So let's see if we can do any of these here. First, let's have a look at this variable named f. Its value is either 0 or 1. And if its value is 1, we set output to true, which means that f also is acting like a flag here. So let's rename it appropriately. I'll quickly run my test to make sure everything works. Now have a look at this flag variable. Every time we have a different iteration of the for loop, flag is again reset to 1 at the top, which means that the scope of this variable flag is just for one iteration of this for loop. Even if we move this variable inside, the code should still work. I'll run my test again to ensure that is the case. Now, why did I do this? Well, I want to extract every bit of this for loop into individual methods. And if there is a variable whose scope is only within the for loop, I want its initialization to be here. So extracting smaller methods becomes easier. I'll also change flag to a boolean. So it will be easier for me to understand what is going on. I'll run my tests again. The next thing I want to do is extract these individual for loops into their own methods. But the problem in extracting these is this variable called flag, which is being shared by both these for loops. I don't want that. I want both these for loops to have their own output flag. And in the end, I can calculate the value of flag based on the output of for loop 1 and output of for loop 2. So let's introduce individual variables called flag 1 and flag 2 for both these for loops. These two will try to mimic the behavior of flag within the for loop, and in the end, we'll compute the value of flag based on these two. I know it sounds a little confusing, so see how I go about doing it. Since flag is initially true, I've introduced a variable called flag1, which is also true. The place where we change flag to false, at the exact same place, I'll change flag 1 to false in this for loop. I'll do the same thing for flag 2 for the second for loop. What this has done for me is it is giving me individual outputs for these two for loops. And based on these two flags, flag 1 and flag 2, I want to now compute the value of flag here. So let me just try to understand what is happening. If this condition is met, then flag becomes false in this for loop and flag 1 becomes false. If this condition is met in the second for loop, again flag becomes false and flag 2 becomes false, which essentially means that flag is going to be false if either flag 1 is false or flag 2 is false. Or if I invert my statement, flag will be true only if both flag 1 and flag 2 are true. So I should simply be able to say flag equal to flag 1 and flag 2. Let's remove flag from these if conditions. As a matter of fact, I can just declare flag here only because it's not changing anywhere else, and remove the initialization from the top. If you are a little confused, I request you to pause the video, go back and try to come up with your own logic for flag 1 and flag 2. I think you will end up with the same thing. But I have an easier way to test whether what I'm saying is correct or not. I can simply run the tests. Since the test passed, I'm fairly confident in what I'm doing. So now that we have two outputs, flag 1 and flag 2, we can extract these two for loops into their own methods. So let me extract the first for loop. I'll call it is condition met because I really don't understand what it is doing internally. Later, I'll try to go through the for loop, try to understand what it is doing, and based on that, rename the method. Notice something interesting happening here. IntelliJ itself has recognized that the second for loop is a duplicate of the first for loop, except for a few variables. And it's automatically trying to replace the second for loop with this extracted method that I've created. So I'll let IntelliJ use its own intelligence and do the replacement for me. And then I'll run the test to ensure that it has not broken anything. So we have two flags. Flag 1 equal to is condition met of I. Flag 2 equal to is condition met of n minus I. I'll run the tests again to make sure I've not broken anything. And now I'll inline a bunch of variables to make things a lot more concise. As you can see, my code is already looking a lot nicer and simpler as compared to before, but I try to improve it even further. Let's look at this method called isConditionMet. Let's try to figure out what this is doing. I'll change the input from I to number to make it easier for me to understand. We can see that we have a flag which is initially true. We iterate from 2 up till the input number. And if number is divisible by any of these numbers, then our output flag becomes false. This is a classic algorithm of detecting if the number is a prime number or not. So let's rename our method accordingly. Well, half the puzzle is solved. We know that one part of this code is trying to detect whether a certain number is prime or not. All we have to do now is look at the outer for loop within the method, do something and figure out what that is doing. And then my entire puzzle will be solved and I'll be able to figure out what this code is doing. But before that, let me quickly run my tests again to make sure I've not broken anything. So let's look at this function called do something. Let me just rename this. It iterates from 2 up till half of the number. And at every step, it is checking whether I and n minus I both are prime. If both I and n minus I are prime for any given I, then the output is true. Otherwise, it is false. So let's quickly write our observations. Find if an I exists such that I and number minus I are both prime. Or if you put it in a different way, find if a number can be expressed as a sum of two prime numbers. So that is what our algorithm is doing. Let's rename our method accordingly. Now you can see that our code is very easy to understand. We take an input called n, then we see if our number n can be expressed as a sum of two prime numbers, and based on that, we output either true or false. Anybody looking at this code, even for the first time, will take less than a minute to really understand what this is doing. And that, folks, is the power of refactoring. Instead of using 15 minutes to just understand what the code is doing, I've used these 15 minutes to understand, refactor, clean up, and make the code easier to understand even for the next person looking at this code. In real life code bases, these 15 minutes that you've saved for the next person keep adding up. And throughout the day, if you can spend less and less time in understanding the code and more time in adding features, then your productivity improves a lot. It also helps you avoid making mistakes. I'll inline even more things to make this code more concise. Now my code is reduced to two more lines, and both of these functions are really small ones. As a last step, if you're comfortable with functional programming, you can use the Java Streams API to convert both these functions into one-liners. I'll show you how it looks if you use functional programming. But the point I'm trying to make is that if I had not refactored these functions in the first place, I would not have understood what they are doing, and I would not be able to use functional programming here. Since I now have them into small, tiny blocks, if I want, I can use functional programming to make them even smaller. But if you're more comfortable with for loops, keep the function as it is. It is already simple and easy to understand. This is how my code is looking after I've changed it to the functional syntax. The total amount of logic in this code is just 4 lines. 2 lines in the main method, input and output, and then 1 line each in the two methods. So you can see how much more concise and easy to understand the code has become just with the help of simple refactoring steps like extracting methods and removing side effects. We can use a tool to actually compare the code quality of the initial code and the final code and validate what we already know, that the code complexity and the code quality have drastically improved with these small refactoring steps that we've taken. We have this tool which we had originally built only for internal purposes, which can take in any Java code and tell you some metrics about how good the code is. This tool is still work in progress. It has a lot of bugs, but it can help us in this scenario to tell us how good our code is. So let's run this analysis on both our initial code and on the final code and see the difference. Let me input the repository URL here. And for the initial code, I'll put in the master branch. The report tells me that I have 3 areas of improvement. Let's see the detailed report. The detailed report tells us that there are a total of 6 violations. While at a file level, our class length and complexity look okay, let's have a look at the main file. Within the main file, our method complexity is over the threshold, our method length is way over the threshold, and our npath complexity is also way over the threshold. For example, the ideal threshold for npath complexity is 10, whereas our npath complexity right now is 38. This gives us an idea of why our code was so difficult for us to understand in the first place. Now let's look at these same values for our final code. I've put in my URL here and I'll put the branch name as solution. Congratulations, there are no issues found in the final code. Let's have a look at the details. All of our values are within the thresholds. Going to the file level, our class and cyclomatic complexities are still within limits. And within main.java, all our methods have complexities within thresholds, method lengths within thresholds, and cyclomatic complexities within thresholds. If you want to compare, in the initial state, our npath complexity of the method was 38. In the final state, the npath complexity of all the methods is just 1. So you can see how just using simple refactoring techniques, we've improved the quality of code by leaps and bounds. I hope this inspires you to actually try these things on your own project also, and let me know how it works out for you.